This question is from GATE Mechanical Engineering paper of 2019. This is question number 48 of set 1. The question is, if 1 mole of hydrogen gas occupies a rigid container with a capacity of 1000 liters and the temperature is raised from 27 degrees Celsius to 37 degrees Celsius, the change in pressure of the contained gas rounded off to 2 decimal places and also assuming ideal gas behavior in pascals is, and also the value of universal gas constant is given here. Now the biggest clue in this question is, or I can say the assumption is that the gas behaves as ideal gas. So we know the ideal gas equation. So from ideal gas equation we know PV is equal to nRT, where P is pressure, V is volume, N is number of moles, R is the universal gas constant, and T is the temperature. Now in the question it is given that the container is rigid. The rigid body means the volume of the container will not change. So the volume given here is 1000 liters. So let's write here, volume is 1000 liter. Now liter is not the SI unit of volume, so we will convert it in meter cube. But for hydrogen gas, the actual conversion will be around 780 meter cube. 0.780 meter cube. Since in the problem it's not given the volume of hydrogen gas, we will assume that the volume of this gas is 1000 liter is equal to 1 meter cube. This is our assumption because this value is not given. If this value was given in the problem, you will be using this value only. Okay. Now it's also given in the problem that the temperature is raised from 27 degrees Celsius to 37 degrees Celsius. So the initial temperature, let's write T1 is 27 degrees Celsius. And in the SI unit, we will convert it into Kelvin. So 27 plus 273, that will be equal to 300 Kelvin. And the final temperature, let's say T2 is 37 degrees Celsius. So that is 37 plus 273, it will give 310 Kelvin. In the problem, the universal gas constant is also given, that is R is equal to 8.314 joule per mole. Another value that is given in the problem is number of moles. 1 mole of H2 gas. That means N is given as N is equal to 1 mole. So from the ideal gas equation, we can write pressure at state 1 P1 into V1 will be equal to nRT1, right? This is at state 1. Now at state 2, from the ideal gas relation we can write P2 V2 is equal to nRT2. Now since the volume is fixed, the container volume is fixed, so V1 is equal to V2. Let's say this is equal to V, and that is 1 meter cube, it's already mentioned. Now we actually needed to calculate the pressure difference, that is delta P, which is equal to P2 minus P1. So if I write this equation, see N, R and V, all three are constant, so we can take it outside, N, R by V, and in the bracket we'll be having T2 minus T1. Let's substitute the value of N, R, V and T in here. So number of mole is 1, the universal gas constant is 8.314, and the volume is 1 meter cube. The temperature T2 is 310 minus 300. See, here we are taking the temperature difference. So it doesn't matter whether you change it into Kelvin or not. The temperature difference between degree Celsius as well as the Kelvin will remain same. That is 37 minus 27 will be 10 degree, and this 310 and 300. So the difference will remain 10. Now let's move ahead and calculate this value. This will come around, this will be 0.314 into 10. Change in pressure delta P will be 83.14 Pascal. And this is our final answer. Now let's go back to the question and write the answer there. So the change in pressure, assuming ideal gas behavior, is 83.14 Pascal. To learn more on ideal gas, you can refer the NPTEL course on thermodynamics by Professor Anand T.N.C. of the Department of Mechanical Engineering, IIT Madras. Hopefully I was able to clear your doubt. Have a great day.